In this video, I'm going to be talking about the half-life of radioactive materials. Radiation is a hazard that affects a small minority of workers in the United States. Workers in the medical industry, workers in the nuclear power industry, mining, and even construction. Some types of construction may have workers exposed to radioactive materials. Now, I said it's a small minority, but it's still a significant hazard. For workers in those industries, it's important to them. For safety professionals working in those industries, it's important to them. And for safety professionals working in those industries, they'll need to become somewhat of an expert on radiation and radioactive material. For the rest of us who don't work in those industries, we may not need to have the same level of expertise as they would have, but we still need a basic understanding of radioactivity to call ourselves a safety professional. This is a concept that shows up on certification exams. And that's the main reason for these tutorials, is to help prepare you for the certification exams. We need to be familiar with the basic concepts associated with radiation. We need to be familiar with some of the quantitative methods associated with radiation. In this video, we're focusing on half-life, the concept of half-life, and we're going to look at some of the quantitative methods that can be used when working with the concept of half-life. But first, let's talk about what we mean by half-life. The time required for a radioisotope to lose half its energy. Now, I am going to be using some terms you may not be familiar with. If that's the case, if you need to go back and look up radioisotope, I would encourage you to do that. But it's a time required for a radioisotope to lose half its energy. Can also be thought of in these terms. In one half-life period, a radioisotope will lose one half of its nuclei. A radioisotope is decaying. It's going from an unstable form to a stable form. And until it gets to that stable form, it's going through this decay process, the nuclear decay process. But that's really going beyond the scope of this video if I get into that too far. Here's some examples of the half-life values or half-life periods for some different radioisotopes. Helium-6 is a radioisotope with a half-life of less than 1 second. So that's on the low end of the half-life scale. Then we go out to uranium-238, again, another an isotope of uranium. 4.46 billion years is its half-life. It takes 4.5 billion years for uranium-238 to lose half its energy, or one half of its nuclei. Again, helium, it's there and gone. So it's so fast. Helium-6. One thing I will go ahead and mention about radioisotopes: every element will have multiple isotopes. Some of those isotopes will be stable. Some of them will be unstable. The unstable isotopes are the radioisotopes, the radioactive isotopes. And helium-6 is a radioactive isotope of the element helium. There are some elements that don't have any stable isotopes. But again, I'm going beyond the scope of this video tutorial. I gotta cut it out or we'll never get through this. What we want to focus on in this video are those quantitative methods that you may need to use on the certification exams when dealing with the concept of half-life. You're likely to see a problem where you'll use this formula and a problem where you can benefit from using this formula. This formula is one that they will give you on the CSP exam. You'll need to remember what the different variables are all about, but they'll give you this formula. This formula here is one that you'll have to memorize, but it's a simple to memorize formula. It might really come in useful on the exam when you encounter certain types of half-life problems or problems related to radiation. Now, this last formula I'm going to show you, we're not dealing with in this formula, or I'm sorry, in this video, but I think I need to make another video focusing just on this particular formula. It incorporates the concept of decay constant, which again we're not going to get into in this video. Because it incorporates this constant, or this concept, I think it needs its own video. So let's go ahead and look closer at the concept of half-life and some of the types of questions you may see on the ASP or the CSP exam. Here's a problem you might run into, or a problem like this. Ruthenium has a half-life of 1 year. How long will it take for a source emitting 1600 microcuries to be reduced to a 100 microcurie emission? Well, I need to talk about curie, what we mean by the concept of curie. The curie is the traditional English measurement unit for radioactivity, or the energy emitted by a radioactive material. And that's the traditional English measurement unit. The becquerel is the modern SI, or international metric unit. Even though the becquerel is the more modern unit, the curie is still used quite a bit by the nuclear power industry, the medical industry, and other industries where they are dealing with the hazard of radiation. Curie is not going to go away for a long time. And this is the measurement unit that you're most likely to see on a certification exam, is the curie. They may throw some problems at you with becquerel, but it's mostly going to be curie. 1 becquerel, just to say a little bit more about it, is defined as 1 nuclear decay per second. 1 curie equals 37 billion becquerels. This is why curie is easier to work with on certification exams. So that's why you'll normally see it. And dealing with these huge numbers, 37 billion for example, is going to be a little bit awkward on certification exams in that context. So I think that's one of the reasons on those exams you see radioactivity measured using curies. Now there are other measurement units that apply to different dimensions of radiation, but for our purposes we're only interested in the curie for this video tutorial. Back to our problem. Ruthenium has a half-life of 1 year. How long will it take for a source emitting 1600 microcuries to be reduced to a 100 microcurie emission? Now this is more of a thinking problem to see if you understand the concept of half-life. There's no mathematical operations really needed. What I would recommend for a problem like this is just write it out. You start with your original emission amount, or A sub 0 if you want to label it. A sub 0, the original emission from the radioactive material, 1600. So after 1 year, what is the emission going to be? It's got a half-life of 1 year. After 1 year, it's going to be 800. After 2 years, 400. 3 years, 200. And after 4 years, we finally get to what the question is asking for. Again, how long will it take to be reduced to a 100 microcurie emission? Just writing it out like this gets us to the answer. It will take 4 years to drop to a 100 microcurie emission. And you may see problems like this, but you may see problems that are a little more complicated than this. And that's what I want to deal with in the next example. What amount of radioactive material will remain after 1 year if the initial amount was 5 grams? There was 5 grams of radioactive material. You'll see that unit used on these types of questions also. And the material's half-life is 45 days. First thing we need to do, and this isn't, we don't have the simple one year half-life. We got 45-day half-life. It's not quite as simple and straightforward as the previous problem. First thing we'll need to do is identify the number of half-life periods by dividing the number of days in the period being examined, 1 year in this problem, by the length of the half-life in days. We got 1 year. That's our focus after 1 year. A half-life period is 45 days. So how many half-life periods do we have in that 1 year period that we're focusing on? There's 365 days in 1 year. Half-life period is 45, so divide 365 by 45. We end up with approximately 8 half-life periods. Once we have the number of half-life periods, we would then use this formula to solve the problem. Talk a little bit about the formula and what the different variables are. N sub t is the amount of material remaining. N sub 0 is the original amount of material. And N, which is an exponent, is the number of half-life periods. So plug everything in. We have 5 grams of material. So we insert that into the formula. And we have 8 half-life periods. Which in this formula, the 8 is an exponent. So 0.5 to the 8th power is 0.004. Bring down the 5. Multiply 5 times the 0.004. We end up with 0.02 grams of material remaining after a 1 year period. And that's assuming the 45-day half-life. Okay, let's look at one more problem that you may encounter and one more formula that you may need to use on the certification exams. This question is not well written. If I were writing a question for an exam, for the certification exam, I wouldn't write it this way. But you will see questions on the ASP, the CSP, the CHST, or other certification exams that aren't well written. That's why I went ahead and that's why I'm including this in our sample problems to help prepare you for the reality that you're going to face with some poorly written questions. But again, this is not the way I would write it if I was wanting to write a good question. But let's go ahead and take a look at it. What radioactivity would remain from 1 curie of cobalt-60 after a 20-year period? Cobalt-60 has a half-life of 5.27 years. Again, pretty simple problem. They'll give you the formula that you need to calculate the remaining radioactivity. They'll give you this formula. You will need to know what the different variables represent and how to use the formula, the mathematical operations. Again, the mathematical operations are simple. It's not a big deal mathematically if you know where everything fits and the order of operations and which calculator key to hit. Let's talk about the different variables. A sub 0, this is the original radioactivity. A is what we're calculating, the remaining radioactivity after a period of time has passed. Ln, which is, we have a term here, a mathematical term that is the exponent of another term. And within this exponent, we have multiple operations that we're going to have to perform. One of those includes the natural logarithm of 2. 2 is a constant. If you use this formula, it'll always be 2. Natural logarithm of 2. Then you're going to multiply that natural logarithm of 2 times t. T is the decay time, or the period of time that we're interested in for the decay to take place. In this example, this problem, it's a 20-year period that will plug in to that slot in the formula. Now t sub 1/2, that is the half-life. That's given to you in the problem. And that's going to be part of this term that will form the exponent for this term. This term that I keep referring to, the E, That's also a calculator function. That's the analog function for natural logarithms. ln natural logarithms. E is the analog for natural logarithms. Again, both of these are calculator keys, no problem, no fancy mathematical operations, just know which calculator key to hit. So let's go ahead and move on, start plugging in our information. Again, we really only have two locations in the formula where we're entering information, the t and the t sub 1/2. For t, again, that's the time period, 20 years, plug that in. Then t sub 1/2, that's our half-life, 5.27 years. Insert 5.27 for the half-life right here. Now we need to do the mathematical operations within the term that we have in brackets. And I'm not able to pull a TI-30 calculator up on the screen here. That's my preferred calculator for certification exams, is the TI-30. I can use this. It will work. The Windows Scientific Calculator, if I can keep it up here and prevent it from disappearing on me at the wrong time. But you can use this scientific calculator for these types of calculations. Now the order that you enter the keys is different with this than it is the TI-30, so I might stumble around here until I get the proper order of punching in the keys. But let's go ahead and talk about this term and get that mathematical operation done. We need the natural logarithm of 2, and we're going to multiply that times 20. So, and I believe the order of hitting the keys for this calculator for that is 2, then times ln for natural logarithm. Then you multiply that times 20. You end up with 13.86. 13.86. For that term there, the natural logarithm of 2 times 20. Now that leaves us with the analog for the natural logarithm with an exponent of 13.86 divided by 5.27. 13.86 divided by 5.27 is 2.63. And let's just verify that with a calculator. 13.86 divided by 5.27 equals 2.629, and I'll round that to 2.63. So now we have 1 divided by this term here that's in the denominator. E to the power of 2.63 is 13.87. Let me show you how I got that with the calculator, if I can remember how to do it. Okay, here's E for the analog of a natural logarithm. Enter that, and that's actually a constant. So when you hit E, a number is going to come up. With this calculator, you hit E, and then you hit the X to the Y power key. And then you hit 2.63, and you're going to end up with 13.8737, which I round to 13.87. Again, this is different with the TI-30. I wish I could pull up a TI-30 on the screen here and show you how to do it on that. If you do want to learn more about using the TI-30, come by the office and we can sit down with the TI-30 and work through these problems. I can give you a tutorial on how to use that particular calculator. But we've got all of our numbers done now except for dividing 1 by 13.87. When we do that, we end up with 0.072 curies at the end of the 20-year period. Radioactivity after 20 years is 0.072 curies, and you can translate that into millicuries. If you multiply 0.072 times 1,000, you have 72 millicuries. So that's pretty much it. It's simple. It's just the calculator is probably the biggest issue, and making sure you follow the order of operations. And let me back up here. Just one more tip. Go ahead and bring this up. You don't want to multiply the 2 times the 20 first. Go from left to right, natural logarithm of 2, do that, then multiply that times 20. You don't want to do 2 times 20 and then take the natural logarithm of that value. You don't want the natural logarithm of 40. You want the natural logarithm of 2 times 20. So that's a common mistake that I see. That's a mistake that I've made. And not just going in, not really thinking about what I'm doing and punching the keys real quick. So make sure you get all the order of operations correct in problems like this. All right, well, I'm going to go ahead and leave it there. If you have any questions about anything in this tutorial, come by the office, give me a call, send me a text, and we'll talk about it.